Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, everyone. Thanks for coming. I'm Madan Muswati from the Research and Software Engineering Group, and it's my pleasure to invite my intern who's working with Todd on something not related to this. He's actually working on doing very fast log analysis, but I think Veselin's interest is in combining PL and machine learning in interesting ways. And he's done interesting work back at ETH Zurich, where he's worked with his advisor, Martin Wechev, and Aaron Yahav on doing code completion using better language models by analyzing large amounts of code. Wesley?
Yep. So thanks for the introduction. And thanks for coming to the talk on code completion with statistical language models. I'm a PhD student at ETH Zurich. And this work for code completion and statistical language models serves towards a vision that we have, that we want to build systems that solve a variety of programming challenges not possible to be solved before by leveraging availability of massing programming data. So these are big open source projects that are out there on the web. And we made these ideas, but recently a DARPA initiative created this term called big code, and we like this term because because our work is about code and it's also big, so we like it. So these systems that we develop exactly want to combine advanced statistical techniques and programming languages techniques. So we have various works at different stages in the pipeline at ETH Zurich. We have statistical code completion. That's a paper that appeared at PODI 2014 this summer. Recently, we got accepted statistical programming language translation. This will appear at Onward in Portland in around a month and a half. The statistical programming language translation works like, think of it as Google Translate and Big Translate. We implemented it for Java and C# and just see what happens if we apply the same approach as what would happen as the approach for natural language processing. And recently we created a new prediction system called JS-Nice. It's predicting program properties. It's used by JavaScript developers. Got quite a lot of publicity and traction. So a bunch of developers hundreds of developers are using it every day. And this system is predicting properties like names of variables and types of arguments for functions. And these are things that were not possible to get before with previous approaches. So what's the common between these systems? The common is that they used advanced machine learning, and they also combine it with program analysis. And what the goal is that we are working towards a foundation that will actually explain how to build such systems and be as a basis of many other possible new applications. So now I'm going to concentrate more on statistical code completion work. There is a paper at PODI 2014 you can read. And it's a system called Slang. So why do we want to build such a system for code completion? Well, because the code completion problem is a hard problem. It's hard because there are many APIs. Almost every library has non-trivial API, more than a couple of functions that are not very easy to remember, to understand by developers. And so we made a system called Slang that is statistical API completion. It learns the API interactions from big code, from lots of examples of using this API, and then suggests completions based on this. So what are the capabilities of Slang? So Slang takes a partial program, or program's incomplete program, where some of the statements of the program are given, and some are missing, for example, because the developer did not know what to complete the program with. So I give a small example here that uses Android APIs. Camera is an API for using the cameras of mobile devices. And media recorder is another API for recording audio and video. And this class is specifically known to be hard. Its documentation describes it as one huge automaton of what happens after calling each method. So in this example, somebody opens a camera, says display orientation, creates media recorder, audio, video source, output format, output file. Then it gives this together with the question marks to Slang, and then Slang completes it. Figures out that camera must be unlocked, then camera must be passed to the media recorder, then audio and video encoder must be set. So what are the special capabilities of Slang that were not there before? So first, we are able to complete statements that involve multiple objects. So this statement involves both the recorder and the camera. On one, we call the method, and the other we pass as parameter. There is a second capability that was not possible with other systems before, is that we will infer multiple statements at once. So we complete this code to setting both the audio and the video encoder, because this is actually the right way to use a media recorder. Cannot skip doing this. And finally, a major capability of the system is that it can predict things, sequences of APIs that it did not see before as is. So we checked in our big training data that such sequence that says camera open, camera set display orientation, camera unlock did not exist in the training data. Yet we were able to figure out by some code that used some of these methods that this would be the most likely completion for such a program. So 3 capabilities that were not possible before: multiple objects, multiple statements, and generalizing to unseen sequences. So the key insight behind the statistical code completion is that regularities in code are similar to regularities in natural languages. So we want to learn regularities like the fact that we create a media recorder before we code set camera of the media recorder. And it's like kind of similar to what the natural language regularities that would say hello is before world. So natural English speaker would not say the other way around. I mean, native English speakers. So we want to learn such natural ways to write software. And so we come to the Slang system. What the Slang system does is that it takes the big code, and for each of the programs in the big code, it performs a specially designed program analysis that could convert the code methods into sentences. Sentences are something that a language model can take. Then we train a language model, and then we obtain something that looks like a database. That is the model we can query for probabilities. As query, it takes an incomplete program, the one that I've shown you before, or another one. It performs program analysis very similar to the one that we do at indexing time. Then we query the language model in order to complete sentences. So once we complete the sentences, we have a...
It knows where the gaps are?
Yes.
So you're telling it those question marks?
Yeah, you put the question marks in the code. Then it completes the sentence, and there is a procedure that must be done that will complete, that you combine these completions. We cannot just take the sentences that are out there from the language model. We have to combine them. And then as a result, we get a completed program.
Question?
Yeah?
Do you normalize variable names and stuff like that, or?
The variable names do not participate in this because the abstraction removes the variable names.
Right. So
we get sequences of APIs.
Sort of often, right? So for instance, like if you have a camera objects, rack or.
We don't care how the object is named. We care what API sequences are called on this.
I see. Oh, okay. So
if you rename the API, it will probably not work. But the APIs are usually stable things, as words.
And you also care about the type of the objects?
No, we actually discard the types, and it still works. So that's why we think this system will be applicable to dynamic languages as well.
So this is just strings, essentially.
Yes, it's strings. It works with words like in language model. Yeah.
So did you find after the fact that those types can, after the fact, if you have multiple potential parses, then the types can potentially weed out things that are at least won't type check. Did you guys look into that?
Yeah, so we discard the types, but it turns out many things type check. So in the end, the correct thing would be to do type checking of the produced result. But even if we don't do it, we are at very, very high precision. So I will tell you a bit more about what we do at the training phase now. So the first component is the program analysis component that transforms programs into sentences. And for this component, I will explain what it does on a small example. So we perform static analysis. Why we perform static analysis? Because we don't have inputs for the many programs that we will index. We cannot run them. So we statically just read the code. We actually look into it as incomplete programs and statically analyze. And then we perform two types of analysis. First, alias analysis, and second, type state analysis. So alias analysis computes a bounded representation of the potentially unbounded heap. So there may be many infinite number of objects in the heap, but we combine multiple objects into abstract objects that represent the potentially infinite number of concrete objects. The type state analysis analyzes for each of these abstract objects possible sequences of API invocations. So let's go to the example. So there are two abstract objects here, me and she. We can probably denote them by the location at which they are allocated, like new x and new y. But I just wrote them as the name of the variable because there is only one variable pointing at each object. So for abstract object me, there are several possible incantations. So the first one is that me is created with the y constructor. So the first word that I write it comes from y, and then I put some subscript init that says this is a result of calling the y constructor. Then sleep is executed on me. So this is the statement me.sleep. And then talk is executed on me. This is the last statement. This is one possible sequence on me. Another possible sequence would be that each will be called between sleep and talk. So if we enter in the if statement, each will be called as well. And so we have this sequence as a possibility. Similarly, for the abstract object she, we write a type state abstraction, we get similar sequence. She is created with the x constructor, then enter is called on she. So this is this statement around the end. And now this is an interesting word. It says she participates as an argument of a method invocation. And it's the first parameter. So we do not only capture invocations on the object, but also invocations where the object was passed as a parameter. This is called multi-object type state. So once we get from a program to such set of sentences, we can capture regularities in sentences. And these regularities in the sentences will be equivalent to the regularities of the API usage. We designed the abstraction to be like this. So if we see many sentences that look like x, init, enter, talk, we can probably learn that talk is often after enter. It's very likely that talk will be called after enter. And then once we get these sentences, we train a statistical language model. Statistical language model is a very widely used natural language processing technique. The goal is given a sentence that consists of some words, W1 to Wn. We want to estimate the probability of this sentence to be part of the language. So we estimate probability of it. Usually this is done by decomposing it to conditional probabilities. So the probability of the entire sentence is product of probabilities of each word given the words preceding this word. So for example, if we have the sentence, the quick brown fox jumped, it's probability of the multiplied by probability of quick given the brown given the quick, fox given the quick brown, and jump given the quick brown fox. Of course, estimating these individual probabilities may be also very hard because this one has to estimate probability of jump given some very long sequence. So there are different types of language models that try to solve this problem by modeling the language as other kind of process. So n-gram language model estimates this conditional probability only based on the previous n-1 words. So instead of word type on all words from 1 to i-1, it's word I based on the words that are only I minus n plus 1 to I minus 1, n-1 words. So example with a trigram language model, probability of jump given the quick brown fox is estimated just by probability of jump given brown fox. And this on its own is estimated by counting how many times these trigrams and bigrams occur in the training data. So this number n-gram is the number of occurrences around the training data. So of course this has problems. Some of these numbers may be 0. There are standard techniques that solve this called smoothing, discounting, interpolation. We apply them. They are standard in the natural language processing literature, so we just use them. There are other types of language models. We also try to train a recurrent neural network language model. This is a recently popular language model because it has the ability to understand very well natural languages. So recurrent neural network can learn dependencies beyond the prior several words. It works like an automaton, a probabilistic automaton. So we have an internal state that changes by depending on the previous internal state and the word I that comes. And then from this state, we predict the probability of word I plus 1. So these are vectors. So each component gives probability, essentially. And we iterate over the sentence with such an automaton. And then in the end, we get probabilities of the next word given all previous words. And such a language model can capture more sophisticated relationships that are further in distance and also probably in meaning. So it can capture, for example, that quick and jumped are somehow related in probability of jumped given a quick brown fox. Maybe if the fox was quick, it jumped, right? So far, I've shown you how do we get from programs to a language model. So we have this training phase, and so now we should be able to perform queries on this language model. So next, I'm going to show you how do we,
So what about while loops? Loops in general?
Yeah.
How do you guys handle them?
Yes.
So how do you handle them?
So yeah, it could lead to potentially infinite length sentences. So we unroll the loops to some fixed bound. Yes. It's actually probably will not matter for the model because we will actually capture the fact that something may execute in a loop already on the second iteration.
But could you learn to introduce a loop that wasn't there before?
No, we do not introduce. Yeah, it's possible that due to over-approximation, there will be sentences that could not be executed. But I don't think this was a problem with the system.
You can't like introduce while because that's not even part of the language model.
Yeah, the while is not, but it could be that there is a while loop or for loop, but there is a condition so that it actually executes only once. And then we will probably generate a sentence that executes it twice.
I think he's talking about filling up a hole in the incomplete
Yeah.
program.
Say one of those question marks has a while loop.
Yes, so the question marks in this system are API invocations. Yes. But we actually experimented with other question marks with slightly modified models, and they seem to work as well. Okay.
For example, you will not, like before using this API, you have to check that the first parameter should be not null, right? You will not be able to identify those kind of patterns.
Yeah, some patterns are not captured. Yeah.
And it seems like introducing a new object that's not even in the program because everything's based on the method calls on an object.
Yes.
So you can't introduce a new object that was never introduced before. And then
Yeah, we can introduce only constants as new objects. Well, this is simple. Once we get the API, and we have some missing methods, we will try to fill them with constants. And we have some missing parameters. So to show how a query works, I give a small example that uses SMS messages in SMS API in Android. So this example takes an SMS manager and a message. It looks in the length of the message. If the length is above certain threshold, it divides the message and then calls some green API, that's hole 1. I constrain this hole to use 2 object SMS manager, at least for this example. Otherwise, it goes into another hole, the red hole, that is completion that should have 1 method invocation, again constrained to 2 objects, SMS manager and message. And so we perform the same type of analysis on a query program like this. We look into the abstract objects, so we find the SMS manager. So for the SMS manager, and then we look into the possible sequences that we can get, while we also include the holes as words. So hole 1 is the green hole. We have a sequence that says get default result. So this result says that this object comes as a result of a method invocation called get default. Then we call divide message. Then we call into the green hole. Alternatively, we get the SMS manager, and then we call into the red hole. Similarly, for the other abstract object that comes as a list of messages, we get it by divide message, and then we pass it into whole one. And the message object, we call length on it, and possibly call divide message. Once we call divide message, this object does not enter in any hole. But if we don't call divide message, this object will enter into the red hole. So we have a sentence that says length h2. So we want to complete the holes, so we discard all the sentences that do not have hole mentioned to them. And for the sentences that include holes, we want to complete them. So how do we complete them? We ask the language model to find the most likely completions. So we do this by looking into bigrams and trigrams that are anyway in the language model, in an n-gram language model. And then we try all such possible bigrams and trigrams. And then we get possible completions along with probabilities of sentences. So the hole may not be only in the end of the sentence. It may be in any place. One sentence may have multiple holes. But we can get all the completions for the sentences. And so now what we want to do is we want to give a result that's the most likely result. One simple way to think is, OK, we'll just take the most likely sentence for each of the completions. And then we'll try to build a result from it. So these are the most likely sentences. So these are some example probabilities. The first, so it completed whole one with set multipart text message here set multipart text message param 3. For the red hole, this sentence completed it with send text message, and this sentence completed it with length. And so we can probably notice that this is not a feasible solution. These two sentences disagree on what should the red hole be completed with. One of them said send text message, the other one says length. So in addition to these probabilities, we have to add strict constraints that will say the words that we complete with should agree between the sentences. And so in this example, if we, for example, want to look into the average probability, by taking this sentence by taking this completion for the last sentence with holes, we would get to a completion that both agrees with the constraints and has the highest probability. So we find
there are two APIs in a single hole, right? One can be a send text message.
Yeah, so
API.
they will look like holes with different colors. I mean, imagine they're holes with different colors. And then for each of the colors, we will expect that the completions agree.
Right, but a single hole might have multiple statements, right? Because you said that.
Yeah, so if you run into this, then you will unroll it into a sentence with multiple holes. Right? And these holes, you will color them differently. Like you call one hole 1, the other hole 2. And then you must have constraints that say, on hole 1, I must agree with hole 1 of the other sentence, and on hole 2 as well.
So doesn't this result in sort of a combinatorial optimization problem where you're
Yes.
going to have to decide on different combinations of things? It could blow up on you with a lot
Yes, they could blow up. But so in this case, we actually made a solver that just iterates over probabilities. Just taking first the most likely sentence completion for each sentence with holes. If it does not satisfy the constraints, we just iterate.
So it's sort of a greedy approximation.
It's not an approximation. No, this is
combinatorial optimization problem to find the optimal sequence.
Yes. So this one is not greedy. It's just maybe slow. It may explode, because if there are too many constraints, we will just iterate over all assignments of sentences for each sentence with holes. Yes?
Why not model it like a constraint solving problem where you have also a cost method, which is from each complete solution, you want the one with the highest average.
So the reason is that the actual instances of this problem do not explode with this algorithm. If you have even if we have 10, 20 sentences, they will probably most likely not be so many constraints. So we will relatively quickly get to a solution that is not infeasible. We will relatively quickly get to a feasible solution. But yes, this is a possibly combinatorial explosion. Yep.
If you have more solutions that satisfy the constraints, do you provide them to the user so the user can choose what he wants to do?
Well, So we have to give feasible solution to the user.
But only there is only one physical solution. Can you have more?
No, there may be more than one. So we actually give more than one solution to the user, but all of them are feasible. All of them satisfy the constraint. So we iterate over the assignment of completed sentences in the order of probabilities, and then we give the top end solutions to the user. So for this example, this will be the completed program. I omitted some parameters that did not involve the objects we talked about. They're filled in with constants typically. And so this is how the combined completion looks like.
Wait, how did you know that send multi-part text message should be a invocation on SMS manager?
Oh yeah. So because send multi-part text message here, it has a word without this prefix, and here it has with prefix. Assume like I wrote. So this word denotes it's a call on this object. There should be also constraint that two sentences should not both say that it's a call on the object. One should be a parameter, the other should be call.
So in some sense, this is encoding the types, right? Because there are only few objects that could be the result of get default.
Yes.
And this is an invocation
Yes,
on that.
this is how it encodes the types without actually having types of information. We get the combined completion. So overall, this is the system. So it takes an incomplete program, performs program analysis, gets sentences with host, completes the sentence, and combines them with a combinatorial problem, like I've shown you before, and then gets a completed program as a result.
So question. So you treat different API call for different objects separately, right? So what the effect if you combine them together into a sentence? So in the sentence there are multiple call different objects. Is it going to be a more precise model, or is it going to be what the effect then?
So in a sentence?
Yeah. So in the sentence you have a sequence of API call for one particular object, right? For one particular type of class, right?
It's for one particular abstract object, yes. Yeah. And so for this object, I would
you have you combine the sentences. Because you have for two objects, she and me, you have two different sentences, right?
Yes.
Now I wonder if you combine the two sequences together into one sentence, what would be the effect?
What would be the effect if we did not do this abstraction?
I can imagine it would be more precise, right?
Because, no, because you actually lose the type information. You actually lose the aliasing information.
But do you capture the interaction between different objects?
Well, we capture it because our sentences are per abstract object. If our sentences were just the whole program, you would not know on which object the thing is called, and then you would have to do some other constraints there for types.
Annotate that object with the type, right? For instance, like she call and then me walk and then she do something and then something like that.
I think what you're suggesting is quite much more complicated. You have many more constraints because you have to say on the whole is annotated, but the words that you are going to suggest, you do not know in these words which object to pass on. I mean, we can probably
me and she examples, and I can make myself clearer.
Yeah.
So
yes.
for instance, in this case, you have two different sentences for me and she.
Yeah.
So I imagine
So you make one sentence that says new X, new Y, sleep, eat, enter, talk.
Yeah, and then for each that thing, I annotate that thing with the class.
Yes, but so the language model cannot take a word with some annotations that are not shared between the projects, because you want that what you get is a sentence that you abstract away the part that is specific for the project, like the actual variables in the project.
So what you're saying that maybe the training data is not enough for inferring that type of sentence?
No, I don't think what you say will actually include words, because you have words with some annotation on the word that says that I pass the object she. So you probably include the name of the object she, or what you will include?
No, the type. For instance, I can do something like she in it and
Yeah, you can include the type.
Y in it and then X slip.
Yeah.
Y slip and then Y it and then.
Yeah. Then you have to include constraints that say, okay, my proposed completion of the whole, it gives me this API should be called with these types. Now you should include constraints. Are there objects that contain these APIs?
Yes. So my question is that feasible? And
It's probably feasible, but it's much more complicated. And I don't know if it will be more precise. I don't think so.
And so in your example, all your holes ended at the end of the sentence?
No.
Right.
Oh, yeah, in the example,
In practice, I guess you can also use information that comes after the hole.
yes, we actually use, there are examples in our training data, in our experiments data. So I showed you so far what the system roughly does. So our implementation is made with Java, with Suit, and with SRILM. And then we trained such a system on 1 million Java methods, which resulted in around 700 megabytes of sentences once we performed the program analysis. Indexed into a language model, it gets to 100 megabytes language model, which for today's standards is not huge. We evaluated this on 84 testing samples. So we actually had to make up these testing samples because they didn't exist. But we make them up from Stack Overflow. We took questions in Stack Overflow and then introduced holes into this question, into the solution for the question in Stack Overflow. Or we took projects that are not part of our training data, and then we randomly introduced holes into the code of this project. We took a method from some project, and then we randomly introduced holes. So in about half of the cases, we introduced more than one hole, just to see what will happen with more complicated cases. And so we run this system, and then we wanted to see if we get the completion that was originally in the code, in the Stack Overflow answer or in the full code. Then we figure out that for around 90% of the cases, the correct completion is in the top 3 results. So we also did bigger experiments, and they also confirm around this number, 90%. We also did cross-validation. The number is even higher there because the code may have duplicated projects. So overall high precision.
The top one?
Yeah, the top one is around 70%. Yes.
Can you go back to the example with sample? Yeah. Okay.
This?
Okay. For example, if I wrote my code with having the first statements in another function code. Okay, so wrap some part of the sentence
Yes.
in a function that I wrote.
Yeah, so right now our analysis is intra-procedural,
Okay.
so we will not take into account, but there are works that do it inter-procedural. And they would capture, if you don't do some strange indirection via some API, it would capture it.
Yeah, but then you would have a problem in your, for example, in your alias analysis, right?
Yeah,
You want to do it in
it's not necessarily giving over approximation of the alias information.
So you said you had 2 different learners, right? So either it's an n-gram model
Yes.
or a recurrent. And
Yeah.
so which one is?
So the best result comes with a combination of the 2 models. Although the trigram language model does almost as good, so I would say it's about the same whether we do combination or trigram. Bigram language model, on the other hand, does not work very well. So we need to capture longer regularities in the sentences.
And so in the sense, there are different ways you can do code completion, right? So for example, Rule just mentioned,
Yeah.
that, hey, maybe we can, not do sentences per object. Maybe we can try different. So did you actually try different things and only one of them succeeded, or was this the first thing that you attempted and it worked?
So we tried a few things, but they were more like variants of this. So we did not try completely different approaches. But I'm pretty sure that approaches like just looking at the program as an AST or as sequences of tokens, we would just not do it because there are long distance relationships that they would just not capture with n-gram language model or even with RNA.
So in that 1 million Java method, how many call are they? Because they are representing the word in your corpus.
Which vocabulary size in the end?
Yeah, so I think the vocabulary is, it's huge, but we actually drop a lot of the vocabulary that occurs only a few times, because these are usually method names that are only local for the project. And so in the end, our vocabulary is around 80,000 words. It could be, it's more than 1 million if we don't drop these. Yeah.
And how much time does it take to complete the whole?
Yeah. So the whole system is quite fast. It takes less than a second to complete, like 0.1 second or less, in fact, for all the examples. And it takes only a few seconds to train the language model, and the analysis is also quite fast. We do Steensgaard style, intra-procedural, field-sensitive pointer analysis, and it takes around 4 or 5 minutes to index the whole database.
So you have 80,000 word,
Yes.
I don't know what that called, but do you think that 80 testing sample is too small compared to that 80,000 word?
Yeah, but so these examples talk about Android APIs, right? So it's essentially what people use in Android. I don't think we can quite make that many more. I mean, we can make other examples, but I already know that in these random examples that we actually built from Android programs, that there were already some duplications of APIs. So.
How did you choose where to remove code and make the queries? And how much was the annotation burden on the queries themselves? Like, did you have to say, I'm going to use this precise objects, or?
Yeah, we said which object, and we did not say anything else.
And how did you choose which sections of the code to remove?
It's random, except we don't remove the word that creates the object.
Okay, so it's random.
Yeah.
And how long did it take? I believe you did it manually, right?
Yeah.
And how long did it take on average? Like, I don't know.
To prepare the data, it took, I don't know, a day, but in order to run it, it was instant, like a few seconds. I mean, it was more time to actually load the model than to perform the query.
Yeah, I'm trying to figure out, like, are these really complex interactions with the API or not? And if they are
some of them are not, others are quite complex.
Okay.
But they're random, so we can expect that some of them will be easy. So just to show you some interesting points, so I show you 6 systems that we trained. So on different amounts of training data, so we take all data or an order of magnitude less data or 2 orders of magnitude less data, and then we also tried to intentionally remove some part of the program analysis to see what will be the effect of not analyzing the programs with an alias analysis in this example. In this case. And so here are the observations. So this is precision for whether the correct completion was in the top 3 results. And so the scale is, so this is this is only 20% accuracy, this is 100% accuracy. And so more data means better precision, like it's clear to see. In fact, data is quite important. But there is another observation that doing the proper program analysis is also as important as the data. So it costs as much as an order of magnitude more data. So what happens is that if we don't do alias analysis on the code, we would get on the training data. What we will get is much shorter sentences. So they will not contain full interactions of an object. And so as a result, we will learn much less from the data. And yeah, it can be seen as a precision. So I would like to step back and tell you a bit more about the big picture. Yep.
So before you go on, you guys have a really nice treasure trove of data now. Have you thought about not looking at holes to help a programmer, but maybe to look at interactions of API design? So for instance, if I start with an init, and I know I want to do something like, I open an object and then I do something at the end.
Yeah.
But there's a very common, if not always occurring, sequence of sentences from init to close.
Yeah, you can put a hole there that is like that says multiple or possibly multiple APIs.
So that should be an API in and of itself, right? I mean,
No, you don't say one API. You can say the whole, and then there may be multiple APIs. And then we will try it with one whole, with two holes, and so on. We will give you the highest.
So if the highest one, my point is though that the use case is not to help a programmer with holes. It's with an API designer to design their APIs. So if I put out an API which is complex,
so what
always use a small subset, then that should be the API.
So what is cool, yes, is that actually this language model captures the
use of the data.
It's not only it actually captures the meaning. I mean it mines the internal type state that the API designer wanted by the API, even though it doesn't know the implementation.
Yeah.
So as a big picture, what happens here? So what we do is we actually train a generative model on code. We are actually learning what is the probability of a program. We do it under abstraction that uses these sentences and the code completion. But our goal was to learn the probability of a program. So we did it by performing program analysis and then language model. Our query was a conditional query. So we have a query program, and then we want to find the completed program such that the probability of completed program given the query program is maximized. And so we do this by our completion procedure. So given program with holes, we get to the full program. So it's very likely that if anybody would do anything with statistics on programs, they would try to make a generative models on programs and try to perform their queries after that are usually such conditional queries. Given a program, find something. So now the question is, of course, what was important for code completion? So why I tell you we did it like this. We have some understanding of the other approaches that will not work. We did not experiment everything, but we know approaches that will not work. And so what was actually important is the question. So the first important thing is the right semantic abstraction. So before this work, there were attempts to just look at the program as sequence of tokens. So they will predict me the next token. And so most likely they will predict opening and closing brackets and stuff like this. But they cannot capture stuff like APIs. Another important observation is that the model generalizes to unseen programs. That's why language models are useful. So there were other approaches that just looked into code and tried to mine some automaton from the function that they see, or maybe even build sentences, but do not put them into a language model. Just remember the sentences, and then when I query, I will look. Well, did I ever had such sentence that will like I have now? So there are systems that do code search, and what they do is that they actually try just to find the nearest neighbor of my function.
So can you be a bit more specific what you mean by an unseen program? Because in your case, you still rely on the bigram and the trigram.
Yes, so the bigram, in our case, the bigram is seen, but the actual query program is not.
So that's what you mean. Right?
Yes. And it's important that we generalize. We actually compared to a system that did code search that just will find all occurrences of some query. They could ask a query like, find me cases where I call this API and don't call another API. And we found that their system was much slower and also did not work in about twice more cases than our system. And of course, we tried it only for small models because we couldn't build. Yeah.
To be clear, that phrase that you just said, it's just the property of the natural language was like.
Yes, it's a property,
model,
yeah,
right?
but
not because of you do something that you have that property.
Yeah, but that's true. We just benefit from the fact that language models are made to generalize. And of course, it's important that everything is fast and precise, so it should be interactive for people to query this thing. And it should be relatively fast to build a model as well. So back to what we do at ETH. So I told you what we do with statistical code completion. You can read about it. We also do other projects. I would like to give you a very sneak peek of what JS9 does. It's currently under submission. I cannot say too much about it, but there are interesting things. You can try the system, it's live. So what JS9 does is slightly different type of learning. It does discriminative model for code. So recall, a generative model gets some program, some big code, performs some analysis, builds some model, and in the end it models the probability of a program. And then there is a argmax query that is conditional. Find me the best result given some query. So this is something that people in machine learning have done a lot. And such kind of systems, I train a generative model, then I ask such conditional queries. But I mean, many will ask, well, if I will ask this query, why do I train this model? It can be quite expensive actually to train this model. Maybe not every application will be as lucky to get to just 2 sentences like language models. And so then there is discriminative model. So in this application, JS9, we predict program properties given a program. So we train a model that learns what is the probability of certain properties given a program. And then we can ask query that is very close to what we learned. And so as a result, we can learn much more complicated model than a language model. So for this, of course, we need that the properties that we want to predict are annotated in the input. So if you want to predict names, we actually want code that has good variable names to train on. If you want to predict types, we want code that has types in the annotated in the training data. And so we implemented this in a system called JS9. You can just go and run it. It's called jsnice.org. So I can show you. So this is if you go to the website, jsnice.org, you get something like this. So you can write a JavaScript program. So I guess you cannot easily guess what this function does, even if I increase the font. So it's called chunk data, takes parameters e and t, and r, I, r, t, something push substring. Well, if I say nicefy JavaScript to this system, what it will give me is code with names and types. So I have the types of the parameters of the function. So it now tells me that the first thing is string and the other is a number. And the name of the variable is str and step. And now I can probably more easily understand that this splits the strings into equally sized steps and returns an array that contains this. So this system is trained on around 10,000 projects in GitHub. For all of them, I mean, we actually removed all the code that did not have good variable names, like stuff that was minified already, for example. And a bunch of projects, I think around, maybe I forgot the number, but I think around 20,000 JavaScript files had types written by the developer. So we learned types from them. And as a result, we can predict these types. So these types here are almost impossible for a current type system to predict, for a current type inference system to predict, because all the type inference works by implication forward. If I know the type of this, maybe I can type check that something is right after that, or infer the types of the stuff after, but I cannot know the type of this variable. So I probabilistically say it's string because of the way I use it. I call substring on it. And I know this is step, maybe because I increment some counter by it, or I use it as some number here. So with this, I'm ready to take more questions. And so thanks for listening.
Yeah. So I like this whole area a lot. So it seems like the two limitations I most noticed here was you have to put those question marks in. I mean, a lot of times people might not know where the code's missing. They just, I mean, would it be easy to build a model that could infer where the blanks should go, as long as I guess you're increasing the probability of the program? And the other is you're modeling method calls but not program statements. How would we extend this to actually be able to introduce and model the actual ifs and whiles and program statements in the code?
Thanks. So we have works in progress for these. So it's true that once we build a generative model of programs, we should be able to answer other queries, not just ones that the holes are in fixed locations. That's true. And for the other question, so the solution is to make slightly different abstractions that would take data flow and control flow into account. So there are such analyses that compilers do. For example, the data flow analysis that will tell me that some variable must flow by calling into some methods, and then the result will come somewhere. This will also capture cases where we want to synthesize expressions that are adding variables, subtracting them, not just API calls.
So are you working on that actively right now?
Yeah. Well, you're not during the internship here. Yes.
So it's interesting that your notion here of types. I mean, it's interesting to think about like what amounts to going on here is a type checker which is probabilistic. If I understand what you said.
Yeah, so we can actually encode strict constraints that will say, well, do not make contradicting types.
Sure, but it's still probabilistic.
But it's still probabilistic. Yeah, we'll tell you this is string, but maybe if there is another class that has the same APIs, it's probably also correct.
Right.
But we cannot know about it.
Yes, I understand. But it's just an interesting way to think about. I mean,
yes,
people go out of their way to build inference algorithms which are precise. By that I mean they're total. They're always correct, right?
Yes,
they're total. Your inference here is by definition not complete.
Yeah,
but
by definition.
Solving a problem that normally people expect to be complete, and so I think that's really cool.
Yeah, it's good.
I mean, what if my C type checker becomes like generics are really hard to type check.
Yeah.
What if you provided a type checker which, rather than giving me all of these things that are actually safe programs, but the type checker tells me no, that's not safe? What if you took a statistical approach where you said the likelihood that this is actually a correct program is high?
Yeah, this is a different problem, I think. So we seem to. I mean, the likelihood to be correct must be trained on something else, not a model of properties given programs.
Why not? Why not take the exact same approach, right? You're just your discriminative model here is just the probability of types given a particular query program.
Yes.
I can give you examples take them where I say that the type checker got this wrong.
Yeah, so you're basically giving me the cases where type checker is wrong.
Right.
Which, makes sense. But
I mean, I hate dealing with generics, so, right,
Well, we do not handle generics in this case. So we have a small type lattice that we run on just to see what happens. But the one that is used for JavaScript type, common JavaScript types, like the DOM arrays, so you see this just says array, although maybe it can say array of strings. So you can probably guess it's array of strings, and so on. I mean, it will guess like DOM element and so on. Yes?
So you said that you focused mainly on Android APIs?
Yeah, for the code completion, yes.
Yeah, so to my understanding, it's really common to have reflection calls in Android libraries. Did that introduce problems for your analysis?
Android what?
Reflection.
Well, we will just see it as invocation to this invoke method. I don't think it will. I mean,
yeah,
in what sense would it be bad? I don't see the problem. We do not want to be sound or precise or something there.
Yeah, but for example, maybe the common paradigm in your training data is to have some object and then get the class and then invoke some method. To me, it seems really generic, so I don't know how you would produce the correct sentences in order to train your data afterwards. I don't know, maybe it's not a problem, I haven't thought about it.
Well, if one specific API is always called through reflection, we're probably not going to learn this API.
Okay.
Yeah.
How is it to realize that the code completion is actually wrong? Because I mean, whenever you're doing this sort of copy-paste coding, you try to at least read the description in the Stack Overflow answer and say, well, you're initializing the structure, whatever you call this API. Well, I believe that this is probably right. But you get just a chunk of code and like it has no annotation, no comment, no whatever. How easy is it to just realize that it's wrong or correct?
So it's probably not very easy to realize if it's wrong or correct, but what we have seen in some cases where we do completions is that it gives correct completion, but maybe for another problem, not the problem that you wanted to solve.
What here is maybe think of comments. Could you put the comments into this and actually produce a language model of the code with the comments and then actually add the comments as well as the code?
Yeah, actually what I was thinking about is basically how extensible is it in adding properties to the stuff that you're inferring? Because I mean, if you wanted to extend it somehow, his idea of using constrained programming or something like that would be really interesting. But you sort of lose most of the information when you chunk it as sentences, right?
Yeah. So the goal there is because we trained a generative model, and it's usually hard to train generative model. It has to be that it's trained on some simple structure like sentence. If you can convert what you want to sentences, like we successfully converted some cases into sentences, then everything will be fine. If you cannot convert your query into sentences, or the property of interest into sentences, but you have some other more complicated structure, like I don't know, data flow graph, or I don't know what. If it's a full graph that you just cannot unroll in some way, which we can unroll, so it's not a problem for this, but then you have more problem to add more information to the model.
Let's thank him again.
Yeah. Thanks so much.